Hello and welcome to part 3 of this video series based on singular value decomposition. In the previous part, we discussed the derivation in detail of singular value decomposition, and also we saw that doing a singular value decomposition of a matrix actually gives a lot of information about the matrix. Primarily, it gives the orthonormal basis of column space, orthonormal basis of the left null space, orthonormal basis of the row space, orthonormal basis of the right null space, and also it tells the rank of a matrix. In this particular video, we are going to actually implement singular value decomposition using all the concepts we have seen so far in NumPy from scratch. We will also use a singular value decomposition built-in function that is there in NumPy, but we will also build it from scratch just to get our theoretical part more aligned with what we are going to implement in Python here. So let's go to Jupyter Notebook and implement this SVD from scratch. So let's import certain package. NumPy as np. From NumPy, import linear algebra. That's a module that we may require as LA. So we have now. So using this NumPy, we will create a lot of matrices. And using this linear algebra library, we will access the eigenvalue decomposition function and stuff like so. So let's take an example of a matrix. Let's say A is equal to np.random.rand. Let's take an example of a 3x4 matrix. So that is that's a matrix A. That's a 3x4 matrix, as you can see here. Let me first compute the two matrices that we need for singular value decomposition. One matrix is A transpose A and other matrix is A transpose. So let's first create A transpose A. That is np dot that is A dot transpose dot A, and that gives the value A transpose A. Yeah. So further, we can also compute A transpose, which is A dot A transpose. So now we have both A transpose A and A transpose. Let's look at A transpose A. That's a 4x4 matrix. Because A is a 3x4 matrix, A transpose A is a 4x4 matrix. Now let's look at A transpose. That's a 3x3 matrix because A is a 3x4 matrix, A transpose is a 4x3 matrix, so A transpose is eventually a 3x3 matrix. One thing that you may notice, that both A transpose A and both A transpose, they are symmetric. So let's see, A transpose A transpose, that is this. And if you see A transpose A, that's the same thing. So because it's a symmetric matrix, similar is the case with A transpose. Now let's compute eigenvalue decomposition of these matrices. So in linear algebra library that we have imported earlier, in linear algebra library there is a function eig that can help computing eigenvalues for any matrix, any square matrix. This particular matrix is positive semi-definite. That will become clear shorter. We already have seen it's a symmetric matrix. Now we will be seeing that its eigenvalues are indeed non-negative, and hence both of these matrices are positive semi-definite. So let's compute eigenvalues. Let's say D1, let's say, and V, that's linear algebra library dot eig function and A transpose A. So that will give us the eigenvalues and eigenvectors of A transpose A. If you see the eigenvalues, D1, these are 4 eigenvalues. So you see this value, then you see this value, then you see this value. And if you see the very last value, you might tempt for, so let me give you the very last value. because that might be confusing. You may think that that's a negative value, so hence the matrix that we have seen A transpose A is no longer positive semi-definite because it has a negative eigenvalue. In fact, the matrix actually is positive semi-definite. What happens here is if you see very closely to this eigenvalue, this eigenvalue is actually has around 16 zeros before this decimal place, 16 or 15, whatever, which means this is really a small value. And these kind of values in Python, both in Python as well as in MATLAB, they represent basically zero, because there are numerical algorithms to do these linear algebra stuff, numerical linear algebra. And numerically, these values are so small, so they are zero. So rather than representing these values to be exactly zero, whatever the algorithm numerically produces, that is this value. So don't worry about this value. This value is practically zero because it is really a small value. It's a value that has around 15 or 16 zeros before the decimal point, which is zero. So so what happens is these three values are non-negative, and 1 0 value, which is the case because the rank of this matrix is 3. It's a 3 by 4 matrix. The rank cannot be greater than 3. It may be smaller than 3, but in this particular case, it is the rank is 3. Now let's test our idea of this eigenvalue decomposition. As we know, if a particular vector is eigenvector, let's see all the eigenvectors here. So this first column is the first eigenvector corresponding to the first eigenvalue. So this is the first eigenvalue. Whatever, I mean, this is an eigenvalue, and the first column is the eigenvector corresponding to it. Then the second eigenvalue, and then the second column corresponds to the eigenvector that corresponds to the second eigenvalue, and so on. So let's see if we have, for example, A transpose A, if we multiply it, let's say with third, or let's say the second column. So that produces this. What is that? That is V. That produces a second column. That produces this particular transform, which means if we also multiply this with D1, 1 multiplied by V, because it's an eigenvector corresponding to this particular eigenvalue, this result should be identical to this result. So let's see. Yeah, as you can see, the two are exactly the same. Sometimes it is possible, actually several times it happens that these values, they are not sorted in any particular order. Let's sort them in descending order, and we will be having, for example, idx equals to np.argsort d1, and I want this sorting to happen in descending order of the values. So that's the descending order, that's the idx index. So now we can sort this d1 as d1 idx, and corresponding columns should also be sorted. So now we have our d1 in sorted order position in descending order. The result actually was this, but eigenvalue decomposition here in Python does not guarantee any sorted order, so it is always a safe step to sort these values. Similarly, the corresponding eigenvalues are. Okay, next we compute the eigen decomposition of AA transpose. So let's say D2, and U is equal to linear algebra dot eig and AA transpose. Next, what we do, we again sort these in descending order with respect to eigenvalues to stay consistent with the eigen decomposition of A transpose A. So what we do is idx, for example, idx is np.argsort d2, and then we have this descending order. So yes, So now we have index, so we have D2 is equal to D2 index, and the columns of U, they should also be sorted accordingly. So yeah, IDX. So now after that, if you see D1, that is this value. If you see D2, these are these values. So you can see the non-zero eigenvalues, because this A transpose, it's a 3 by 3 matrix, it has maximum 3 eigenvalues. However, the fourth eigenvalue of A transpose A is 0. The non-zero eigenvalues, they're exactly the same. And here you have this U, matrix U, that you need. You have matrix, you have this D, singular values, whether you use that through D2 or D1, whatever, that matrix. And now you have V as well. So one clarification here is the eigenspaces or the eigenvectors of both A transpose A and AA transpose. They have, I mean, they're not unique. They sometimes have this sign ambiguity. So you can pick multiple. You can pick, for example, a different basis in V, and that is also a perfectly fine basis with matrix AA transpose and A transpose A. So, and there are sometimes there are numerical stable ways to resolve these sign ambiguities to, if you want a reconstruction back. Now we are going to use the built-in singular value decomposition in NumPy, built-in function. And let's compare our findings of U, D, and V with the built-in findings. There may be a sign ambiguity, a sign catch, but the values, other than the sign, they will be the same. So let's see. So let's say we have U2, let's say S2 and V2 is equal to linear algebra dot SVD, and we do that SVD on A. Remember this V2, the SVD function, built-in SVD function returns this last matrix transposed variant in the last matrix. So we have this V as it is. This V2 will be the transposed variant. So let's see. Now let's compare U with U2. So that's our U, that's our U2 by built-in SVD. So you can see the values are exactly the same. The sign so the sign for last eigenvector is the same. The sign for center eigenvector is different. The sign of first is also different. As I told you, there is always inherently there is a sign ambiguity, which has, and there are ways to resolve it. Now let's focus on S2. That's S2. Now let's see D2. You can see there is a difference because this S2, these are singular values. They are values after square rooting the eigenvalues. So if we take the square root, for example, D2 star 0.5, if we see that, you will get the value exactly equivalent to exactly. So this value, so if you take the square roots, these are the singular values. So these are the singular values in front of you. Now we can compare our computation of V, which is V. So we computed it as, we computed it as V. So V dot transpose, that's V dot transpose, and that's the return value from the built-in function SVD. As you can see, the values are exactly the same. In some places there are sign ambiguities, however. Here you have to see the sign ambiguities in rows rather than columns, because after taking transpose, these are the rows that are in eigenvalues, eigenvectors. So see, for example, the sign of first eigenvector is the same as the first eigenvector here. The sign of second one is different. The sign of third one is also the same. And sign of fourth one is, it has sign ambiguity at this particular place. So with these kind of sign changes, the sign changes are inherently there. There are stable ways to do that. One thing that I want to mention, if you multiply this U times S times V, you will get your original matrix A back. So let's do that. Before that, we build a matrix, let's say D2, which is np dot diagonal S2, that makes a diagonal. And to make it consistent with the rest of the dimensions, let's add a column of zeros, np dot zeros, 3, 1, and we then do it like np dot h stack, horizontal stack. So that's our d2. Now if you see, if I multiply u2 dot this d2 dot this v2, remember this v2 is already in transformed variant, that result, what's the problem? Object has no attribute v2, oh sorry, that's dot v2, and this result should exactly be the same as the matrix A. So you can see the matrix A, this is matrix A, and through singular value decomposition, we reconstructed A exactly like we did. So yeah, further you can see this U, V, they are orthonormal. So if you see, for example, U2 dot U2 transpose, that should be identity matrix, and you can see the only diagonal matrix is non-zero. The rest of the values are zero, practically zero, because these values are zero because 10 raised power minus 17 is really, so all the off diagonal entries are zero. Same goes with v2 dot v2 transpose. That is also, if you see that, that is also the only diagonal entries are non-zero, rest of the entries are zero. Same goes for whatever we have computed. For example, u dot u transpose, that is identity matrix, and v dot v transpose, that is also identity matrix. So here I have implemented singular value decomposition using eigenvalues and eigenvectors, and I've also shown you a built-in function that is there in linear algebra library in NumPy, which is SVD, and I have shown you that our implementation and the built-in implementation is exactly the same. The only catch is resolving the sign ambiguity, and there are numerical ways to do that. So yeah, so that was about implementation of singular value decomposition. So I hope to see you next time with more fun stuff with these kind of videos.